let's take a look at this one. So when we do statistical analysis, and once you have prepared your data set here, right? So you look here, this is the code. So there are a lot of code. What? So, hello. What? Huh? Oh, really? Just hide. Yeah. So how can I see you if you are not here? Let's resume. Now I know F12. Okay, thank you very much about this. So let's come back here and one more time. So look here. Basically, we all start from the analyze, the data analysis of here, right? So this is a regression. Regression and SPSS 14 only offers two different kinds. But if you go to our virtual cloud server in Wenzao, you will see a lot of different process over there, right? So let's make it simple. So let's just get this one. So once this pop out, you will see there are several columns. But as a minimum, you need to put a dependent variable here and at least one independent variable here. And as we try to identify the linear relationship between two variables, right? So remember, each of the variable has to be at least ordinal. You cannot use nominal variables to put here, because overall there's one very important presumption here. Basically, we are trying to use trying to do this. We have a y equal to ax plus b. So the thing we talk about here is about the formula. So this is a formula indicate the relationship between two variables, right? And this one, x, is called independent variable. And this one, y, is called dependent variables. So basically, the x change will make y change too. So this is the linear regression. Linear regression, the relationship between x and y is determined by the a, we call beta. And this one is constant, and this is beta, okay? So, but anyway, just remember, y equals ax plus c plus b is something we try to use simple linear regression to produce. Sometime, of course, if you put two independent variables, then you would have something like this. That is, y equal to ax1 plus bx2 and plus c. So you see, now we have two independent variables, right? So let me make this a little bit. Okay, so this is the right way to do. So basically, let's see this one. There are two independent variables, but all point out to a dependent variable here. So the change of x1 and x2 will change the value of y. That's it. So most of the time, for now, you only focus on this one. The change of x will change the value of y. And the relationship of y is, and x is y equals a times x plus b. And you will be amazed to find out this formula, although it is very simple, but after you conduct a simple linear regression analysis, you will be able to identify a lot of message on this. One, the value of x will tell you. Number two, the value of b, you will know. And number three, it does not include here, but it indicates the strength of A, the power, the statistical power of A, the statistical power of B. And whether, and the other one is whether we could have a formula, whether we could a formula like this. So the very simple process for using simple linear regression analysis can tell us a lot of information about this equation. So now let's move back here. So now if you see here, this is something we call dependent variable, right? So basically this is y. And here is something you put for x. And there is a presumption for using this. That is, both y and x must be at least ordinal variables. Remember that, okay? So it must be, has a ranking hierarchy over there, at least. You can use 1, 2, 3, 4, 5 to make the difference. So there must be some sort of differences in terms of ranking, at least. Remember, at least. So you cannot use nominal variables to conduct this kind of simple linear regression. Because for nominal variables, the number 1, the number 2 serve only one purpose, tell the difference, but not the ranking, but not the order, but not anything else, right? So if we want to calculate ordinal variable is the minimum requirements for you. So this is very important. So now, let's do a little bit. So we can just go there. Let me go to check the. So if we have a pay base, and let's say if we have okay, English. There's here we have this one. The English proficiency level. And you can see there are 3 different levels, right? So it's roughly, and this is a middle level is a proficient. So there are 3 levels. So basically, this is an ordinal variable. So I want to try to see whether X is the English proficiency level and the relationship between the pay. So let's go to the pay. So where is the pay job? Okay, here. So this is the base pay. So base pay. So I want to see, let me see. So if this is Y, this one, pay base, we have a pay base. We treat it as a Y, right? And this is LEN, this is X. So did you see the relation between these two? I want to check whether English proficiency, the different level of English proficiency has a relationship with the so-called the basic salary, month salary you can have from the job market. So these two, pay base, Y and LEN is the English proficient level. So now I'm going to use this. So now I'm come here. So this is a simple linear regression. So as we say, we have to put dependent variable, this one, right? Pay base. Did you see that? So I go to find out the pay base. Okay, this one. So pay base. And I continue to identify English language proficiency. So this is one. So now we have 2 different variables, right? So again, this is X, and this is Y. This is the minimum input you need to put into the column here. So for simplicity's sake, we do have a lot of choices out there. For example, statistics. Statistics, you can have a lot of different statistics over there, right? But you don't have to get trouble for so much. And of course, if you like to draw charts, you can do that. And because you have no idea about the Z-score yet, right? So you don't have to bother yourself. But now let's talk about this one. As we know, we can pass the syntax, right? So we can just pass the syntax. So look here, this is the syntax, regression syntax. So we can use this syntax to produce, for example, now let me try to use this syntax to produce the output. So I highlight it and I Control R, Control, push together. So Control R. So this is the result. This is the result for the output. The output. Okay, now, normally, when we have the statistical output from SPSS, remember, we do not just copy and paste, right? And if you do that, you just miss the point. And basically, we have to carefully select some of the numbers here so that we can report the result. So what are the numbers we need to include? Well, basically, it's over here. But now, just for your information, we need to know this R square, the number here. And also, we need to know the degree of freedom and the significant label. And F value, this is F value, based on the degree of freedom of 1 and 1864. And the probability for this one is 0, almost, okay? And the other one is, look here. This is English level, right? And this is the base. So how can we do this? Because we have to look at this one, this, and this, and this too. That's it. But now you may be a little bit confused. What does that for, right? Okay, but it's okay. Let's take a look at about what would be the proper format for us to produce. I will go here. I will come here so that you will be much easier for you to know, because you need to write some examples out there, right? Look familiar, right? So see, this is the output, right? And remember, I put here just for the convenience of lecture purpose. When you write up your report, never put this on your paper. I emphasize again. Never. Don't do that. This is wrong, okay? And because I just want to let you know how do this number come out. Do you see this one? Okay, so I want to compare. Let me compare of this, and I make this as this smaller so that I can. So you may want to look at your own monitor. That would be much easier, right? So I write it out. So look here. Basically, we have conduct statistical analysis, right? Most of the time. Remember, most of the time. The report for the result is only a very short paragraph, just like this. Just like this. It's not a lot of fancy tables. You don't need it. You don't need it. So it's just this. So let's look at the way of describing the output. First of all, you have to illustrate the purpose of the test. So the relationship between English proficiency level and the expected salary was investigated using simple linear regression. See? The purpose, the way. So this is very standardized. And it was found that English proficiency level significantly predicted expected salary. And this statement, let's see this one, English proficiency level significantly predicted expected salary. And the parenthesis here is to provide evidence. So now, let's think about this. Can you find out where is the so-called this number? Anyone? Can you identify? Let's go through here, and our purpose is to identify beta. So where is beta? This is beta, not R. Okay, beta. And where is beta? Do you see that? Here. Beta. And the significance of level is 0.007, which is less than 5%, right? When we say there's a significant difference, we have to judge. We have to compare the p-value to the alpha value, 5%. If this is less than 5%, then we have to reject the null hypothesis. So let's see what is the null hypothesis. Null hypothesis, basically it means a hypothesis of no difference. No difference, okay? No difference. If it is less than 5%, then we have to reject the null hypothesis, because the null hypothesis is saying that there is no difference, right? So we reject there is no difference, then we have to accept there is difference, okay? So this is a very simple way to make this. So basically, p-value is the most important part for us. And let's see. Here, let's come here. We say it was found that English proficiency level significantly predict expected salary, and the beta value is 0.078, and the p-value is 0.007. And you can find out the two numbers from here, right? Okay, so now let's understand what is the beta means. The beta refers to, let me, now be careful. The change of one deviation of English proficiency level, one, because this is X, right? And this is Y, right? This is Y. So one change of the standard deviation for X, one change of a standard deviation for X will make a change of 0.078 change of Y. That's it. It just means that, okay? So let me say that again. One change of the standard deviation of X, here in this case is English proficiency level, will make a change of 0.078 standard deviation of expected salary. And this kind of relationship is strong because the p-value is 0.007 is less than 5%, right? So the relationship for this one is significant. So for when we report our data, we only, let's look here. We say it was found that English proficiency level significantly predicted its expected salary. And hey, what is the evidence? Give me the evidence. Now, this is the evidence. Okay? You get it? So whenever you have a statement in statistical analysis, you identify the evidence. So here, let's see, the statement here, right? And statement. And we have evidence. And this is the key evidence. We do not to, see, let's look here. We don't need to pop out the whole table. We don't need. Because all the other numbers does not relate to the statement. Our statement saying that the English proficiency level significantly impact the expected salary, right? Base salary. So you have to identify the evidence from the table. The output here is first two, one is beta value. The other one is significant label. These two are coincide with each other. So once you point out, okay, so thank you very much. You have identified the evidence, right? So I agree upon with you that this statement I will accept. You get it? So now, let me reflect the process of reporting one more time. First of all, you have to identify the purpose of the analysis and the methods. So here is the purpose, right? The relationship verb was investigated with using, so this is the method. So first of all, once you lay out this, and then people will know, okay, you are trying to understand whether there's a English proficiency level as Y, X, and expected salary as Y, right? Okay, and what will be the method you use? You use simple linear regression. Very simple. Remember, once again, it's very important for you to keep in mind, that is, most of the statistical analysis, when you see the output, you need to report, right? And the report is often just within several sentences or at most one paragraph. It cannot be a full page. The one you have produced previously for chi-square test, right? Few pages. Basically, they are wrong. They are wrong. But just give you some idea about, we will start from the rough draft to the refined version of reporting. So remember just that. And when you want to do chi-square or cross tabulation, and when you test the relationship, most of the time you only report chi-square. Okay, you only report chi-square, and why you want to use it, and what kind of way you use to, and what will be the result. Next. Okay, so once we have this, we identify the relationship between X and Y, right? Okay, so we try to identify the formula, the equation. So the fitted regression model was, let's look here. Expected salary, here we have Y, right? Y is equal to constant plus times this one. Okay, now it seems that we just changed the order. We just changed the order. That is, we have a B plus AX. Well, if you want to say is Y equal to A plus BX, it's up to you, but it's the same. This is constant, and this is coefficient. Constant, coefficient. So now I want to compare the number. So let's move down a little bit. So we have the 35179 as a constant. We have a 3607, 09, sorry. 09 as the coefficient, right? Where are the numbers? So look here. We have the number over here, right? This one. And this is here, beta, B value. This is beta, standardized coefficient. This is unstandardized B, but it's okay, we just call it B. And this refers to the constant. So look here, constant. And the other one is 3609, and did you see this refers to 3609, right? So if we use, then that would be much easier for us to know. We know we are trying to identify Y equal to X plus B, right? This is normally. So Y basically is the expected salary. Is that right? Okay. And X X refers to English proficiency level. And A, how about A? A refers to this B value. So this is A, right? And how about the last one? The B value, constant, refers to this number. So this is B. So now we have a whole set of equations, right? Do you see that? So now, we just simply move or just write the number and then fill into the equation. We try to use this one, right? So basically, y equals to x plus b. Y, the expected salary is equal to A is this one, 3609 or 3610 times this English proficiency level plus this one, 35179. That's it. So this is what we have for the equation. So basically, this is the equation, right? Next. It seems that we have an equation, but not all the time we can use the equation. Why? Because we have to make sure both the constant and the B value for constant and the B value for the English proficiency level is significant for us to use. So how can we make sure that? First of all, we make sure is A significant enough to put over here? Well, here. It's good, right? Let's correlate this one. We want to identify this one to see whether it is good enough for us to use. We find out this is less than 5%. Great. Okay, so we use it, right? So we accept this one. And how about the constant for B constant? We have found out the 35179 and the significant level is 0. Wow, it's good too, right? So this is good, and this is also good, which means that this equation is good too. So we can use it. But remember, sometimes, although we can always produce something like this, right? We can always produce something, but not necessarily these two p-values are significant. If these are not significant, for example, the significant level for this one is 0.6 too high, right? And for this one is 0.32, and that is too high. So basically, we cannot accept A, we cannot accept B, right? So there is no equation, which means X, the change of X, has no impact on the change of Y. That's it. So basically, we cannot have equation at all. But sometimes, let's think about another scenario. Be careful. That is, sometimes we could have the p-value here is significant, is less than 5%. But here, the significant level for this one, let's say, is 0.22, is higher than 5%, right? So basically, this means the change of X does have an impact on the change of Y, but the constant has no effect. So basically, we will have no formula like this. We cannot use it because this one cannot stand there, right? So we do not have the equation. However, the change of X still impacts the change of Y. The only thing is that we do not know the constant. What would be the correct constant for us to use? So we do not have this. Okay? So basically, there are three scenarios we might have. That is, first, we can use the simple linear regression to create an equation, provided that both the both significant level are significant, are less than 5%. Sometime the other one is both of them are not significant, more than 5%, then we will have no equation at all, right? But some other times there's kind of mix over there. Sometimes this is significant, but this is not. Or this is significant, but this is not. In this case, we have to judge. We have to judge whether if the significant level is justified, is valid for the constant. It says nothing. But it says nothing because we are more curious. We are more interested in understand the change of x on the change of y, right? So constant is not necessarily matter, does not necessarily matter here. So we will pay more attention to the p-value for the beta. Okay? So now let's move on to see this one. Once again, you see. So we know we have this, so we provide evidence, right? And again, the fitted regression model, so we have an equation. So y is equal to the constant plus coefficient times English proficiency level. Okay, that's great, right? Okay, suggesting that for each unit increase in English proficiency level, expected salary increased by this number. Okay, so let's see, we have 3 different levels. 1, 2, 3, right? So if you are 1, then there's a 1 plus this. And if you are 2, then it's this plus this times this. And this times 3, this, right? Okay, so we have an equation here. And the number for the equation come out from the table. So we just put them over there. And once you have identified the regression, you have to explain what does that mean. So this is suggesting that for each unit increase in English proficiency level, expected salary increased by this number, okay? So now we have finished the 3rd job, right? And the end to talk about this one. So now you talk about the model was statistically significant and accounted for 0.6% of the variance in the salary. Okay, now. This is the conclusion, right? It says that this one is significant, all the word. But where does this number come from? Let's try to identify the number here. Strange. I want to do this. Okay, number. So let's see the number again. So look here, the model, so we have a conclusion, right? The model was statistically significant and accounted for only 0.6% of the variance in salary. It's not big, but if you look at this 0.007 is significant, right? But now we need to know where the number is. Okay, let's try to identify it. First of all, where is R square? R square. This one. Do you see? R square, right? Handicap. So R square, right? Okay, how do we have R square? Because it come out from here, R. This is called as Pearson R. Pearson R indicates the strength of the relationship between 2 variables. It's not strong, but it is significant. Remember, it is not strong, but significant. So now you can use your smartphone to use the calculator 2 times 0.078 and 0.78 and have times 0.78. So see, you can see it's equal to 0.006, right? Okay, so they are related. So here is something we need. So this is the only thing we need to provide the information here. And the next one is to identify F value. F value refers to the distribution of the variance. Normally, the larger the variance, the more significance of the differences. But indeed, we have the so-called F distribution table for us to check out. But now you don't have to do that because it's all done by computer. So now, let me tell you what does this mean. This means that when we try to identify F value, and instantly you will see this one, 1, 1002, 1200, right? This indicates 2 degrees of freedom. 2 degrees of freedom. One is the regression. The other one is the residual. And let's say, when we say degree of freedom, now, did you still remember what does it mean to say degree of freedom? Last time when we learned a chi-square cross tabulation, right? So basically, it is about very simple. That is, if we have 4 people here, if we control 1, then there are only 3 persons who can move around freely, right? So this is degree of freedom. That's it. So it's always -1. But if there are a lot over there, such a cross tabulation. So if we have a 4 column and 3 rows, then we control 1 and we have a 2. So the degree of freedom for the cross tabulation is 2 times 6, 3 equal to 6. That's it. And it is a useful indicator for us to understand the distribution and the disperse of the data. That's it. So every time you have to, if you want to identify the real probability of F value, because this one is very huge, right? 7.398, and you consider this 1 and 1,200, and the number is here, and the corresponding number for the F value here is 0.007. See, this is point. So now we have the number over here, right? Do you see this one? They are all required to put due. Okay, so basically we do indeed. We have a lot of output coming out from here. That's too huge. So we do, right? But we are not using all the numbers out there. And never just copy and paste, but because this is very amateurish. Okay? So remember, the number you really need is very, very simple. Sometimes it's only here, here, and here. That's it. And of course this. This is for you to talk about variance, explain the variance. This is for you to talk about the equation. Okay, so now I will give this back to you, and please use 5 minutes of the time to go through the process by yourself. Before that, let's take a break and come back at 4:10. The second one is a writing sample showing significant relations between X and Y, yet the constant is not significant. So there is a slight change for the wording. First of all, we identified the purpose and the method used in one sentence. A simple linear regression was employed to investigate if the expectation of having the right to vote predicts support for lowering the voting age, right? So basically we have 2 variables. One, the expectation of having the right vote predicts support for lowering the voting age. So a significant regression equation was found, and so we identified the number here. So the number, look here, basically it talks about the variance. So the variance shows here. Let's see this one. So F value equal to 14.1. So we have degree of freedom, and value is here, and the significant level is here. So here, right? And the R square is equal to this one. This means that Y, the value for X has 46% of 46.3% of the ability to predict the value of Y. The variance refers to the estimated value for Y. 46%, 46.3% of value for Y can be predicted exactly by X. That is the idea, okay? And the relationship is significant because it shows here. So this is evidence, right? With an R square of this. Although the regression model, we have a regression model again. So regression model is here. Y equal to constant plus coefficients times X, right? Was not fully supported. Then you have to explain why. So here is why. Let me get it a little bit smaller, and I will broadcast one more time. So let's see this one. We say this is a little bit not supported. So although the regression model support for lowering voting rate, this one is the regression model, right? Was not fully supported because P for the constant. So here, for the constant is 0.764, right? So this is evidence. So basically, the style of reporting statistical report is always identify the fact, provide the evidence. Identify the fact, provide the evidence. On and on, that's it. Very simple, right? So this is the fact. We know it's not fully supported. Why? Because we know P for the constant is this one, right? Okay. And this still implies that with each unit increase in the expectation of having the right to hear. So look here, we know there's a significant level. So the change of this, if this is changed, then we will have the change for the support of lowering the voting age by this one. So this is good, okay? So the green part stands, but the yellow part does not, so you have to say that. So basically, can we use this formula to predict the output for X, for Y? No, but we know there's a strong correlation between the change of X and the change of Y. Okay, get it? So this is one way to say it. And now let's move up to, if there's no whatever kind of relationship, so we can just do this. A writing sample showing no significant relation between X and Y. So if there's nothing at all. So again, we report. A simple linear regression was conducted to access the relationship between the feeling proud to be a Taiwanese citizen and the belief that poor political conditions are self-induced. Two variables, right? Okay, so however, the model was not significant. Why? And evidence. The p-value is this, so high. So there's no relationship at all. And accounted for only 1.6% of variance. We have this one, right? R squared. And furthermore, the predicator variable, pride in being, predicator means independent variable. This Taiwanese did not significantly predict the outcome. Why? We say on standardized coefficient B of this, a standardized coefficient of beta, this, and the t-value of this and this that shows there's no relationship at all. Okay, so overall, the results suggests a weak and a non-significant relationship between the two variables. The same. And let's move down a little bit to tell you. Let's take a look here. It's very important to understand when we have the beta, right? And of course, we want to understand how strong, how significant the relationship between for the beta. And we found out the significant level is only 0.610, is more than 5%, right? But how do we come out of this p-value? How? Basically, it is based on the t-value. T-value. Okay, so now I want you to check out a t-value table from the smartphone. Now, you can just use the Google phone to check. T-value table and two-tailed. Okay, let me use this one. Come on, do something by yourself. Check it out. Okay, something like this. Check it out, okay? So if you check this out, then of course we can just go there. So you will see that when we test the probability, there are always a lot of t-test, f-test, t-test and f-test and a chi-square. There are always tables there for you to determine the probability of the happening. Probability of happening. For example, if the degree of freedom, how can we see this one? Well, basically, let me enlarge it. This means if the degree of freedom is 10, see, we always need to have two numbers, right? One is degree of freedom. If this is 10, and if we want to have the t-value probability lower than 5%, so let's see, this is 100%, right? So going down here. This is 5%, two-tailed 5%. And if we want to have one tail, then this is the one we are looking for. Okay, let's see this one. So what will be the cutting t-value? That is here, 1.812. If the t-value is higher than 1.812, then the probability will lower than 5%, just like this one. Did you see that this is greater, right? And did you see the corresponding t-value? We want to have the p-value here is smaller and smaller, right? So this is the cutting point. But now, what is t-value? Well, t-value is the difference between the mean variance. But it's okay, there's always a distribution over there. So this is the so-called t-table. Before the computer age, we have to check the t-table to determine the probability. So let's assume this. If we have found out that the degree of freedom is 13, and the t-value is 2.160. What would be the corresponding p-value for this? Then we can check here. Oh, it's around 2.5%, right? If the t-value is something like this one, then the corresponding will be just like this one. If this is two-tailed, then this is the corresponding p-value. It's too huge. So in one word, in short, the larger the t-value, the lower the possibility. So if we have a t-value this big, then the probability will be less than 5%, right? So let's come back here to see the t-value here. Did you see that the t-value is 0.5? Very small, right? Very small. So normally, well, if you are used to it, when I see the t-value here, I could have a sense. The probability should be less than 5% because this is large. And this one is smaller, so it's unsurprisingly, the p-value is large, right? Can you see this one? Smaller, large, and larger, and smaller. And if we check out the t-table, it has the same tendency. If you look at here, this one, smaller, right? So the probability is higher, and larger, the probability is lower. But of course, you have to consider the degree of freedom. That's it. And we have an F-table. We have a chi-square table. We have a z-score table. We have a lot of tables out there. Fortunately for us, we just look at one very simple number. That is this one. Only look at the significant level. Okay, then now let's try to understand what is the p-value actually mean. What does p-value actually mean? P-value means the probability of the null hypothesis to stand true. Again, the probability the null hypothesis to stand true, which means we have to accept, right? If the probability to stand true is higher than 5%, then we accept the null hypothesis. If it is lower than, less than 5%, we reject the null hypothesis. But if we reject the null hypothesis, then what we should do? Let's say this one. First of all, we have a null hypothesis, right? So look here, we have a null hypothesis. So basically, we try to decide whether we reject or accept it. Is that right? There are only two choices. So basically, if we accept, then null hypothesis stands. Then when is the occasion we choose to accept null hypothesis? When the p-value is greater than 5%, then we accept. We don't argue about that. But in the case when the p-value, this kind of p-value is less than 5%, for this one, less than 5%, right? Then we have to reject the null hypothesis. Then if we reject the null hypothesis, then what we should do? Then we have no choice but to accept the alternate hypothesis, which means H1, the hypothesis with difference. Okay, is that complicated for you? You must have learned this last semester, right? You? A little bit, okay. Please enlarge those a little bit to be this big and that big and so huge, then it will become part of you, okay? It's very important that hypothesis testing is all about whether you need to reject or accept the null hypothesis, right? You get it? You get it? Great, bravo, you know. That's smart kid, all of you. So basically, let me first time in my life to write the whiteboard, okay? So take a look. Okay, so basically, when we test, we do start with the null hypothesis, right? Null hypothesis, we call the hypothesis of no difference. No difference. So basically, we try to decide whether we need to accept or reject, right? So basically, there are only two possibilities. No, research question normally is the alternative hypothesis, something we try to prove. But there's a huge but. Why do we need to have the null hypothesis? Why? Because normally it's very difficult to prove something is true. It's impossible. It's not possible for us to prove something is true, right? So that is why we use falsification. Remember the meaning for falsification? Ring any bells? Ding dong, ding dong. No idea. My goodness. Where did you learn your methodology? Who told you? Oh, my roommate. I got it. Okay, fine. The progress of science is made possible by falsification, but not verification. You have to remember that. Falsification means that when we have something, try to prove, right? But theoretically, it's not possible to prove something is definitely, completely true. It's not possible in theory. Let me give you some example. We all know that the shortest distance between 2 points is the straight line, right? So how can you prove this is true? Well, in theory, you have to draw all the infinite number of the line, one at a time, until the end of the infinity, right? But the problem is that when we call that infinite number, that is unlimited possibilities out there. So you have to draw all the nine there. So every time, if you try to prove this is true, it's theoretical impossible. Theoretical impossible, right? Okay, you get it. So now, verification is not the driving force for us to advance science. It's not possible. But how can we make ourselves to move forward in the scientific world? We use falsification. Falsification means that every time we spend one effort for an experiment, right? Our purpose is not to prove it. Instead, our purpose is to make it wrong, to falsify it. So let's see this one. Instead of prove the shortest distance of the two dots is a straight line. Now, we try to find out a scenario that can falsify this hypothesis. So Einstein says that in the relative comparative theory, that in the universe, the shortest distance between 2 points is not a straight line, right? Because if you consider the curved spaces, right? If we have a space in the universe, let's think about the universe. So in the universe, something like this one, so it's curved. So if we have 2 points here, right? 2 points here. So if we just follow the plane, then the straight line will be here. The straight line will be here. But no, it's not. It's not. Because according to Einstein, the relativism, we know it is about here. The shortest line is something else. So remember, the hypothesis is nullified, is falsified just because of one theory or one experience says that it is not in this case. So in this case, we have to revise the hypothesis, right? So now we have a new theory about the shortest distance between two dots. That is, we have to add in one condition. That is, in a plane, in any plane, the shortest distance between two dots is the straight line. Because in universe, it does not exist in this way, right? So we have to change it. That is how we advance our science, falsification. So to make it short, that is, it's not possible to verify, but it is much easier to falsify with one experiment. Falsify. Okay, so now, let's go back here. So if we say, so whenever we conduct statistical analysis, we always try to find out the p-value, always. Because in the end of any kind of statistical analysis, we always have a p-value of there, right? And the p-value, we only look at the p-value, and we have to determine whether we have to reject or accept something. But we know for one thing, our purpose of statistical analysis is not to prove something, but trying to falsify something. The something here is the null hypothesis. Null hypothesis equal. So we try to falsify the null hypothesis. And the other side of the null hypothesis is the so-called alternate hypothesis. Alternate hypothesis in our research, sometimes we call it as a research hypothesis. The real stuff we want to do. But we do not focus on this. Instead, we talk about this. So now, our tryout. We know we have to accept or reject, right? So basically, our choice is very simple. In terms of statistical analysis, the choice is very simple. We look at the p-value. If the p-value is greater than 5%, then we say, okay, we accept the null hypothesis, right? Because null hypothesis and alternate hypothesis are logically one. What does that mean? It means in all scenarios between two variables, or in this scenario, there are only two possibilities. One is null hypothesis. The other one is anything else, right? So the anything else is alternate hypothesis. Null hypothesis is this one. So if we accept this one, then what happens? We accept, then we have to reject this one. Is that right? If we choose to accept this, then we have to reject this one. So this one wins for this time, because the p-value, if the p-value is greater than 5%, then we accept this one. Then how about if we found out the p-value is less than 5%, then what happened? Well, the probability for you to stand true is so low, right? Less than 5%. So I have to reject you. So I choose to reject you. Then if I reject you, then the possibility for this one is gone. Then the only choice I have is to accept this. Right? Do you see this? So first of all, we look at the null hypothesis first. We use p-value to make our decision. Whenever it is greater than 5%, we accept the null hypothesis. And when we accept the null hypothesis, then there's nothing for us to talk about this one. No need, right? But if we reject, we reject it, then there's no choice for us. Remember, the tone of the statement is just like this. Since we reject null hypothesis, so we have no choice but to accept alternate hypothesis. No choice but to accept. It seems that we are so reluctant. Remember, we are reluctant. Okay, because this one is gone, so this is the only one I can accept. And remember, until now, I did not say null hypothesis is true or false, right? And I did not say alternate hypothesis, H1, is true or false. No, I don't say it. I only say that I reject or I accept. Reject or accept, it means that this is based on the result of one test. One test. But the beauty of falsification is that once the null hypothesis is rejected, it has to be revised. Is that right? If one hypothesis is rejected based on one simple test, then the connotation, the context has to be revised to accept another time of the test. You get it? Let me give you one example. For example, in this morning, I walk out my door, and I found a small puddle on the side of the electric pole. Small puddle. Okay. So, small puddle. So I collect the information. So I assume. I put a hypothesis for this one. This one is made by a small dog's pee over there, right? Okay. So this is my hypothesis. So I need to test it. So I go there. I went there and use my tiny finger and put a little bit and test. Come on, scientists. Scientists always do this, right? So I tested, a little bit salty, smelly like pee. Okay, it is pee. Made by a dog, maybe a dog. I'm not so sure a human being or dog, but it is pee, right? So after I test it, my hypothesis, it is made by a dog, peeing over there, right? And I test it, it is pee. Tastes like pee, smell like pee. Fine. So this time after the test, I cannot reject my hypothesis. So I accept it for now, for this time, for now, okay? So the hypothesis I just gave you stand for one time. But I don't feel that's quite right because you point out it may not be dog, it may be human being, right? Okay, so I need to go through another round of tests to test the hypothesis. But the point here is that the hypothesis I raised when I see the scenario this morning do not need revision so far. It stands true. Remember, it is not really true, but stand there because I accept the hypothesis. Do I need to change it right now, revise it right now? No, because my test does not falsify it. So, okay, fine. So my hypothesis stands here. Some dog pee there with a small pot of water over there. And it is a pee from a dog. Okay, I don't feel quite right. So I want to challenge my hypothesis again. So I tour around, and I asked, have some interview, data collection, some interview. Really, no kidding. The first one I tested is data collection, right? So based on data I analyze, I accept the hypothesis. Second round of test, because I don't feel fine. I'm a scientist. I want to do some experiment. Now, this time I don't do experiment. I interview. I interview the big brothers, big fathers, and old dads, old mothers, old moms walking on the park, right? And say, hey, did you see any dog walking around the park this morning and have a pee here? They said, no. Then why this? And some of the witnesses said, oh, it's a small kid peeing over there. Okay, fine. Are you sure about this? And the lady said, yeah, I doubt. So I go to collect another set of data, interview Tim, and you happen to be there. So, no, yeah, indeed, there's a pee. It's me, you. Well, it's confusing, but definitely it's not a dog, right? It's not a dog. So we have two contradictory witnesses. One is it is done by Tim. And the other one is done by a young kid. And this is the verdict statement coming out from the old lady. Although these two are somewhat contradictory, it's not really conclusive. But one thing for sure, it is not made by dog. It's a human being. So here, I have to reject my hypothesis, right? Because one test has falsified my hypothesis at first. So if I want to continue my experiment, I need to revise my hypothesis. That is, based on my preliminary research, this part of water is not made by dog, and very possibly made by human being. But who is the culprit? I need to continue with my exploration. That is how we advance our science, folks, right? So one thing for sure, just give you some idea. When we say we are scientists, we always try to falsify the hypothesis we raised, instead of proving it, because it's not possible. It's not possible to prove that our hypothesis is true, but it is very easy for us to falsify it. So falsification is the very power for us to advance the science. The same here. Remember, how can we falsify the null hypothesis here? Use p-value. And how can we generate the p-value every time, just like something here? How can we generate it? You don't have to do anything. So far, you don't have to. The only thing, you just look at the number, right? If you look at the number, now I know, I look at here, oh, 0.013 is less than 5%. So the constant B, unstandardized B for constant, is significant. But this is not an issue, because we are more interested in understand whether there's a correlation between these two, right? And it says this one, no good. So too high. So we have to accept there are no relationship between these two. Null hypothesis means no relationship, right? So these two, there's no relation, so we have to accept. And then there's no relationship. And then we have to ask, why do we have the number here? Because it come out from here. And what does this mean? I just give you the t-table, right? So every time we determine the p-value, it always come out from some t-table, f-table, or chi-square table. That's it. No mystery. But lucky for us, and fortunately for us today, is that we don't need to calculate that. The only thing we need to know is to identify the p-value. So you need to how to use p-value, okay? P-value always come out from t-table, f-table, chi-square table. Always, no exception. There's always a number corresponding to the probability over there. Okay, before the computer time, you have to check out the t-table. But now, you don't have to. You just look at the number and say, hey, oh, okay. And no relationship. And based on this, you can provide your statement. Okay. So far, are you good? Okay, so I'll give you another 5 minutes to look at the second example. And I have changed some of the wording here, so you may want to change your writing to, here is the sum of the change. This one, take a look. So this is a new writing here. Some change. Take a look and make a necessary change on your own. Now, for you. Do you know how to come out of this? Okay, now, let's come here before. So this is the output, right? So you need to use your tiny fingers, 3 fingers. Control, Alt, and S. Print together. Oh, but no, I'm sorry. Control, Windows, and S. Strange. Oh, I forgot. Ah, sorry, my bad. Okay, use Shift, Window, and S. Press together at the same time. Once you press it and use your mouse and do this, And then you copy this image. And you come back to your Windows, your Word. And then you can find the space here and Control V. Then you will have it. Let me repeat the process for you one more time. In the window, you have to copy and paste. You need to take this out, right? So Shift and the window and S all together. And then once you have this, then you can use your, and just, that's it. And you can come back to your Word and paste it, Control V. So do it by yourself. Try it. Any, you can do this. Okay. Oh, no. When I ask you to use a cross tabulation, right, you need to compile. You have to edit the number data and put it like something you created, right? And you still remember the first one, you have to include several output, the number from several output, right? So you cannot just copy and paste. But here, I want you to provide this for evidence, for me only, okay? So I want to know, you wrote this. For example, you wrote this statement, this paragraph here, and the paragraph is based on this output. So I want to see the output for the evidence to evaluate whether the numbers you put here are authentic. But remember, in real writing, you cannot put this. Once again, let me say that again. Read my lips. Don't put this into your writing, your formal writing. If you do this, you fail. But for next assignment, if you don't do this, you fail. So funny. Okay, get it? I think you got my point. I just want to have some proof that your numbers are legit, okay? And so, because you need to produce this, so you have to go through your file. And remember, it will be a little bit difficult for you to find the 3 different scenarios. One, no relationship. Second is with relationship, but the constant is irrelevant. Third is that you can create an equation fully, right? So you have to go through your file to test the different scenario. So throughout the test, you will get some experience of using it, okay? So that is my purpose. So you have to find the 3 different scenarios by yourself with your data. If you cannot find any from your data, you may want to use some of the test file from SPSS. SPSS has some files out there for you to use. Just go to Explore, play around, and you will find out to fit in the 3 different scenarios. Okay, so this is your task. Any question? If no, just enjoy your day. If you want to stay, that'll be fine. You can come to ask me. If you want to go home, just go. If you want to go home to cook your meal for your wife, you can go. I'm talking to myself. Okay, so you can do, in other words, you can do whatever you want to do from now on. But remember, this assignment is due by the end of Friday. One more time. I know that you can do it, so just go home and enjoy. Any question? So if no question, you can pack up and go home. And if you want to ask me, please welcome. That's bad. Very bad, very bad. People are not so friendly nowadays. They have zero tolerance for this kind of practice. No. Test. Scientist.可以吧？
很高哎、
可以了啦，第三高了。那没关系，偶尔高也有低，这很正常。
老师，那个你说那个是截图，
对啊，截图。
screenshot 怎么用？你说是按
这个 Shift Control 然后 S，
哦，OK OK，
然后你就可以拉了截图。Shift Windows。
哦哦，Windows 哦。